Configuration is resolved using a very simple approach. The configuration was supposed to be easy to maintain and to extend. If new properties were to be considered, that should not involve refactoring a large number of code lines. We defined a direct relation between the parameters we wanted to be configurable and the names of the parameters in the configuration. We decided to store the configuration in files in ini format. This format describes a set of pairs of property names and property values. So, in one side we have classes with internal variables and their values. On the other side we have a configuration file defining the values of these variables by using exactly the same names. The only thing we needed to implement was a way of passing the pairs of values from the configuration file to the classes. We defined the configuration interface, which offered getters and setters to read and write parameters from it. The design took into consideration two different implementations for this interface, one that would read its parameters from an ini formatted file, and another one would maintain its values in memory to be used in unit tests. Modules can fetch configuration parameters from instances of this configuration interface. The interface does not interpret those parameters in any way. It simply delivers pairs of values. The module selects the correct ones and the user has to define them in the configuration file. Parameters that are not defined in the configuration file are always assigned default values. An SDR application that follows the channel architecture pattern can define an almost infinite number of flow graphs, but in our case we wanted to implement the model of a GNSS receiver. That model has a specific form and a specific number of parameters that can be applied to it. So, for instance, we know we need instances of specific modules: data conditioner, GNSS channels, PVT, output filter. Connections between modules are always the same. The configuration system we've already explained let us associate implementations with modules. For that, we use the module name, the parameter name implementation, and the name of the class implementing it. This information is interpreted by a factory class which encapsulates the complexity behind the instantiation of modules. So by passing the configuration to the factory, we receive an instance of the required module using the correct implementation. The flow graph itself does not instantiate modules. This separation allows adding new modules implementations in the application by simply modifying the factory. Because of that, the flow graph can be implemented in a very simple way, where it only has to pick the instances from the factory and connect them, constructing the model of the GNSS receiver. Once the flow graph is built, it can be started and signal processing can begin. During running time, many things can occur. Satellites are discovered, signals are lost, channels get activated, etc. All these events, and many more we can't anticipate, will take place, and the flow graph will have to react to them in some way. For this, we decided to use an external entity to control the flow graph. This entity would receive events from different sources. The control would then apply actions based on these events. How does the control receive the events? We defined a thread-safe queue. This queue would be shared by the control entity and the rest of modules that needed to generate events. If a module generates an event, it lands in the queue and will immediately be available for the control. Control can read it and take the necessary actions. Since the queue is thread-safe, there are no conflict with the many modules generating events at the same time. The GNSS-SDR project made use of well-known software methodologies and tools to ensure quality on the resulting software. Coding guidelines, test-driven development, peer review, sharing information through a wiki, control versioning, release, build and test procedures, unit testing, integration testing, bug reporting, etc. The project had a very detailed schedule. It was defined to contain all necessary tasks to achieve a complete GNSS-SDR application. The team members were in various locations, Barcelona and Berlin. We maintained a communication level with the required quality by holding weekly meetings held on Skype video conferences, setting up a mailing list, and shared folders on the internet that contain articles, books, documentation, and even signal samples. A workshop was set up one weekend in May in Barcelona. During that workshop, the software modules were tested in real environment using different test hardware, and the team members were able to work together. This diploma thesis work began in February and finished in the end of May. During these 4 months, the project has produced the following outcomes. It has produced C++ source code. This code is located at an SVN repository, including the standard folders for branches, tags, and trunk. The software was never branched, but has produced 7 tags until the last stable version, which is 0.3.1. This version includes various artifacts. First, the main binary executable. It is called Mercurio, which was the nickname for the project for the team members. Version 0.3.1 of Mercurio includes the configuration, flow graph, and control systems as explained in the design. The configuration system is implemented by an interface, configuration interface, and 2 implementations of this interface are included, file configuration and in-memory configuration. File configuration reads property names and values from a file in any format. In-memory configuration does not have a source for its parameters and is empty after instantiated. This in-memory configuration implementation is used in unit testing to avoid dependencies with the file system. The flow graph system is formed by the GNSS flow graph class, the GNSS block factory, and a set of GNSS block implementations. The GNSS flow graph defines a public interface to start, stop, connect internally, and to apply actions to the configuration of the flow graph. The GNSS block factory is used internally by the flow graph to instantiate modules. The factory offers public methods for that. GNSS blocks are what the design considers modules. These blocks are an aggregation of new radio blocks that form a specific flow graph. GNSS blocks encapsulates the way new radio blocks are instantiated, connected, or configured. This way the flow graph can interact using GNSS blocks and the configuration system. Version 0.3.1 of Mercurio provides several implementations of these GNSS blocks. Some of them were used for testing purposes, and they have no real GNSS application. But it does provide the implementation for 4 modules that are useful for a GNSS receiver. The file signal source is used to introduce signals in the flow graph that have its source in data files. It is able to cut the stream of data after n samples have passed through it, and it also can dump its output into a file. The USRP signal source does a similar job, but the source for the samples is a USRP front end. As with the block for files, it can cut the stream after n samples and dump its output into a file. The GNSS block direct resample is an implementation of a signal conditioner module. It is able to increase or decrease the sampling frequency of input signals in a very efficient way. As with the rest of modules, it can dump its output into a file. The last GNSS block corresponds to an acquisition module. It is able to detect the presence of satellite signals and send a control message with the corresponding event. Its output can be also dumped into a file. All the features of these blocks can be managed by the configuration system of the application. The control system is provided by the control thread class. This is a very simple implementation which instantiates a flow graph, starts it, and then remains on an infinite loop until the flow graph finishes its calculations. During the loop, control thread checks the control queue to look for events and trigger the corresponding action. The project also provides unit testing for many parts of the code, as well as a build procedure using the Boost build library. This library provides a build tool similar to new make, but aimed to have a clear syntax and better portability. At the moment, the code is compilable under Ubuntu 9.10, but it could be ported to other environments easily. Complete instructions for building the application are also provided. The project has also made use of some C++ open source libraries from Google that have implemented important aspects such as logging, profiling, or unit testing. The GNSS-SDR project aimed also to provide knowledge about how to develop a complete GNSS-SDR application. The team has gained a valuable experience. Although this work is framed within a diploma thesis, the project is still alive at CTTC, actually searching for funds and presenting further results to the research community.